In this video, we are going to look at explaining why some ligands are weak field ligands and some ligands are strong field ligands. So I've pulled up this slide from a previous video, just instead of making this slide again, just to look at what we did in a previous video. So we've got this idea of a free metal, a transition metal, a first row transition metal. Whether or not it has 4 electrons, like in this example, is irrelevant, but we have the 5 degenerate d orbitals. We have the barycenter going across here, which is constant energy. And then in a weak field, a weak octahedral field in this case, it's split into the EG set. There's two of the 5 d orbitals are up here, the dz squared and the dx squared minus y squared. And then below the barycenter we have the T2G set, which are the dxy, dyz, dxz. And we have delta O here because it's small, relatively small. It's less energy than the pairing energy. So rather than pair, we promote from the T2G to the EG rather than pair up in the T2G set. And then over here, when we have a strong field, then delta O is actually greater than the pairing energy, so we preferentially pair. So rather than promote, we pair up, and that can lead to different electron configurations. So here in our D4 example, in a strong field or low spin complex, we would have an electron configuration T2G4. Whereas over on the left, in our weak field high spin complex, the D4 would have an electron configuration of T2G3 EG1. Okay, well, let's try and look at the origin of this now. And the origin comes from pi donor and pi accepting ligands. So let's have a look at pi donor ligands. Essentially, pi donor ligands are going to give us weak field versus pi acceptor ligands, which are going to give us strong fields. Okay, so I'm going to try and get this all on one slide so we can do a head-to-head. So we've got pi donor, and our candidate here is going to be the chloride ligand, but any halide would suffice. So let's see. We have the EG set and the T2G set. Let's pick just one electron. So let's say we have an electron here in our T2G set. So this clearly is our octahedral field splitting here. So we have a D1 metal, split in an octahedral field. We have a ligand, let's see, over here. So this is going to be P6. So we have 6 electrons because it's Cl minus, so remember that's 1s2, 2s2, 2p6. So that's where I'm getting this from. So we'd have Hunt, 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 Pauli, Pauli, Pauli. We've got our 6 electrons here. And because of the interaction, the similarity in energy level of the T2G set from the metal and the ligand p electrons over here, then we would have an interaction of these orbitals into a bonding and an anti-bonding set. Okay, now because the p electrons, because these are the, let's say this is the metal, this is the complex in the middle, and this is the ligand on the right. Because the ligand is lower in energy than the metal in this pi complex, so these are pi electrons here, then they're going to funnel in and fill the complex's energy level here. So Hunt, 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 single fill, double fill, Pauli, Pauli, Pauli. So these 6 ligand electrons have already filled in. I'm going to label this. The labels are not important for us in general chemistry, but I'm going to call this T1U. T just means there's 3 of them. 1 means it's the first one. U means ungerade, but we're not really interested in that right now. Yes, I know you read. That's nice. Okay, go away. Oh, I've just hit the eraser. Okay. Okay, so because these 6 have already gone in here, the metal electron has no choice but to go up here. So maybe actually I should do the metal in a different color. I'll do the metal green. To keep it distinct. So that metal electron has gone up here. So let's continue this diagram. Now the EG set is just too far away. So this is T1U, this is T1U star. So in effect, this T1U star has become the new T2G. So in effect, what we've done, because of this pi donation of the ligand electrons into the complex orbitals. Okay, I need you to go away now. We've effectively made delta O small. And we know that that's now going to be less than the pairing energy. Okay, so again, it's the preferential donation of the ligand electrons. So let's try and write something in words. So pi donation leads to decrease in delta O, which leads to high spin complexes. Okay, let's look at pi acceptor ligands now. And our example of a pi acceptor is going to be carbon monoxide. So carbon monoxide, let's start off again with our EG and T2G. Our EG and our T2G. So we could have, I'll try and remember to use the same color coding. That's our original delta O. Let's put our electron in, and now I've just forgotten to do it. Let's do it in green. So there's a D1 in green. So this is going to be our metal. We're going to have our complex in the middle, and then we're going to have our ligand over on the right. Our ligand, however, is the pi electrons are empty. So instead of a full pi, we have an empty pi. So we can accept into the pi, but we can't donate from the pi. Okay. So we've got nothing to donate with, so the metal electron is free and clear to go down into the complex. And so we've effectively made delta O larger. We could label some of these again. T1U, that's effectively now T2G. This would be T1U star. Okay, so we've effectively made delta O larger. So we could say pi acceptance leads to an increase in delta O, which leads to low span complexes. It's hard to say more without going beyond what would reasonably be expected in general chemistry. But this is just to frame this conversation about weak and strong field ligands. So we've got a way to explain the fact that we have this difference in splitting, and we obviously connect that back with the spectrochemical series. Okay, so we can actually start to quantify some of these differences. So the next thing I would like to do in this video is to calculate crystal field stabilization energy. So let's start to look at crystal field stabilization energy, CFSE. Crystal field stabilization energy. So crystal field stabilization energy is 0.4x minus 0.6y multiples of delta O, where x is the number of electrons in a T2G set, and where Y is the number of electrons in the EG set. So for example, so let's see, for a D3 ion in an octahedral field, the crystal field stabilization energy is going to be, well, let's see what this would look like. Let's put the electrons in, I guess. Hunt, hunt, hunt. So we've got our T2G set, our EG. Remember the barycenter's here. This is plus 0.6 above the barycenter, and this is 0.4 below the barycenter, where the barycenter is in the middle here. Okay, so the crystal field stabilization energy is going to be 0.4. Now, how many electrons do we have in below 0.4? We have 3. So I guess I'll just rewrite that a bit. So we have 3 lots of 0.4, and then I'm going to subtract from that. Well, I have none above, so it's no lots of 0.6. So that's going to be positive 1.2 multiples of delta O, 1.2 lots of delta O. Okay, so that's my crystal field stabilization energy. Now, obviously, whether you're in a strong or a weak field is going to impact you. So let's have a look. Now, it didn't apply for a D3 ion because you can't use a D3 ion to tell the difference between high spin and low spin. But what if we had something like D6, which was sensitive to the difference? So let's look at CFSE of a D6 in delta O, and we're going to compare weak field and strong field. So let's compare those two. So we could have, I guess let's do them side by side. We'll do the weak field here. Weak field, remember, is high spin, and the strong field, remember, is low spin. We've got our EG set, our T2G set. Make this a bit bigger, our EG and our T2G. So let's put our 6 in, so hunt, 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 jump, 4, 5, 6. So we have T2G 4 EG2 versus our strong, because don't forget here we have delta O is less than the pairing energy. And here we have 1, 2, 3, 4, 5, 6. So we have T2G6, and that's because delta O is greater than the pairing energy, so we pair. Let's look at crystal field stabilization energy. So CFSE here is going to be 4 lots of our 0.4, and we subtract the destabilizing effect from that. We have 2 lots of our 0.6, and that's going to be multiples of delta O. So 4.4s are 1.6, 2.6s are 1.2, so 1.6 minus 1.2 is 0.4, multiples of delta O. Let's just remind each other why it's high spin again. It's all good practice. We know that the spin is the sum of the spin quantum numbers. So right now I've got 5 upward facing spins and 1 downward facing spin. So that's 5 plus a halves, or net 4 plus a halves, because I've got 1 minus a half that cancels one of them out. So S is going to be plus 2. And here, if I did my CFSE, my crystal field stabilization energy, I've got 6 0.4s, I've got no 0.6s, multiples of delta O, so that's 2.4 delta O. So a lot more crystal field stabilization energy for the strong field D6 complex. And again, it's low spin because we have essentially 3 upward facing spins, 3 downward facing spins, so they equal 0. And 0 is definitely lower than plus 2. Okay. Let's see. Let's see what else we can talk about in this video. 24 minutes in. Let's see. Okay, so we've had a look at that. Let's now move on to look at how experimentally you would determine high and low spin based on spin-only magnetic moment. That would be definitely a topic to pursue at the general chemistry level. So, determining high or low spin from the spin-only magnetic moment. Which I'm going to call mu. Okay, from the spin-only magnetic moment, which I'm going to call mu. Okay. So spin-only magnetic moment, mu, is 2 s, where s is spin, s plus 1, all square rooted, and the units are mu b, where mu b is the ball magneton, and the ball magneton is the charge on the electron, h bar, over twice the mass of the electron. Okay, so it's got units of magnetic moment, but we're just going to call it mu b. Okay, so let's see an example. Manganese 3+ coordination compound was measured with a spin-only magnetic moment equal to 4.85 ball magneton. So is it high spin or low spin? Is this complex, or is this compound high spin or low spin? And we'll assume it's in an octahedral field. Okay. So is it high spin or low spin? Well, let's look at the contenders. So let's say it's low spin. Let's say it's high spin. And then let's look at low spin. Okay, if it's high spin, well, first of all, manganese 3+ is, I guess we'll do this in red. Manganese 3+ is a D4 complex. So let's have a look at a D4 complex. If it's high spin, it's going to be T2G3 EG1. And if it's low spin, it's going to be T2G4, right? So we know how that's going to work its way out. If it's high spin, then looking at this formula up here, the spin-only magnetic moment, mu, is going to be the number 2. Well, we need to calculate S, because I need to plug in S. So if I've got 3 upward pointing arrows, 4 upward pointing arrows, then S is going to be 2, right? So 2, the number 2, and then S in this case is 2, and then S again, which is 2 plus 1, square root the whole thing, multiples of ball magneton. Well, this is going to equal 4.9 Bohr magneton. If we consider the low spin alternative, let's calculate S. So S, well here, we'd have, if we've got 4 in the T2G set, then one of them is pointing down and 3 are pointing up. So the down pointing electron cancels one of the up pointing electrons, and we have 2 up pointing electrons remaining. So spin is 1. So the spin-only magnetic moment would be the number 2, and now the spin is 1. So I would have 1, 1, plus 1. The whole thing square rooted, multiples of Bohr magneton, and this would equal 2.83 Bohr magneton. So to answer the question, if these are the theoretical outcomes, and this is experimentally what was actually observed, then clearly it points towards that outcome. So this is evidence supported. So we would conclude on this occasion, this particular manganese compound is a high spin complex. Just because this number is closer, the theoretical number for the high spin is closer to the actual experimental value. Okay, so that's how we would do it. Let's have another couple of examples. Okay. So here's another example. So the magnetic moment of this complex, Mn, so it's another manganese compound, but we're told it's NCS 6 4 minus is 6.06 Bohr magneton. And this time we're asked, what is the electron configuration? Right, so that's the question. What is the electron configuration? We know that this ligand has, so NCS is a negatively charged ligand. So we can figure out what the charge on manganese is. That's the first thing we need to do. So whatever the charge on manganese is, let's call it X. And there's 6 negative charges on the NCS ligand. So manganese charge plus 6 single negative charges on the ligand overall is equal to a negative net 4 charge. So that means that the charge on manganese, X, minus 6 is negative 4. So we can just add 6 to both sides. So X, in this case, equals plus 2. So I have manganese 2 plus, and that is a D5 complex. Okay. Okay, same idea as last time. We want to figure out whether it's high or low spin. It's just asked in a different way, but the only way to get the electron configuration is to know whether you have a high spin or a low spin. So we're going to ask the same questions. High spin, low spin. Okay, well, if it's high spin, spin-only magnetic moment is going to be the number 2. Well, remember, if it's high spin, we should write the potential electron configuration. This would be T2G 3 EG2, and the other contender is T2G 5. They're the two options, right? Which is it? Let's figure out what the spin is first. So here S, well, I've got 5 upward pointing arrows, that would be 2.5. And here I've got 3 upward and 2 down, so I've got just spin a half remaining, so 0.5. So high spin 2.5, low spin 0.5. 2.5 is higher than 0.5. Okay, spin only magnetic moment is the number 2. And then the spin 2.5, the spin again 2.5 plus 1, all square rooted, multiples of ball magneton. And this works out to 5.92 ball magneton, which is looking pretty good. Measured 6, theoretically calculated 5.9, so that's a good contender. Let's see if this is any better. Spin-only magnetic moment in this case would be the number 2. The spin 0.5, the spin again 0.5 plus 1, all square rooted, multiples of ball magneton, and this works out to 1.73 ball magneton. So we have a clear winner. The 5.92 theoretically seems to explain the data better than does the 1.73. So we have evidence that this complex is actually high spin, and so we have evidence that the electron configuration is T2G 3 EG2. And not only that, but we've also learned, if this were an unknown ligand, we've also just learned that NCS-, we have evidence that it's a weak field ligand. Okay. So we have evidence that that's a weak field ligand. I think in this next, slide, I think I'm going to summarize the different types of spin-only magnetic moment, just so that my students have answers to check. Okay, so I don't know if we can fit this all on one slide. Maybe we'll, let's see. Yeah, we can. Okay, so let's have D1, D2, D3, D4, D5. Okay, so let's try that. So D1, how am I going to look at this? So D1, it doesn't matter if it's low or high spin, it's always going to be the same. So we would have spin-only magnetic moment. Now I've used a slightly different calculation here. Let's see. Yep. Okay. Sorry, I'm just talking to myself. Okay, so we have, this is going to be 2. And then if it's only one electron, it's going to be 0.5 plus 1 square root Bohr magneton, which I think we just said was 1.7 Bohr magneton. Okay, so Bohr magneton. All right, we're cooking. 2. This is going to be 2. 2 halves is 1. 1 plus 1 square rooted Bohr magneton. This should equal 2.8 Bohr magneton. 3. We have 2, 1.5, so 1.5, 1.5 again, plus 1, all square rooted Bohr magneton. That should equal 3.9 Bohr magneton. 4. Now, 4, actually, I'm going to get rid of 4 here, because so far 4 and 5, so far 1, 2, and 3, we only have the problem of high spin, right? We don't have to worry about high and low spin. 4, 5, 6, and 7, we have the option of high spin and low spin. So let's not do 4. Let's do 4 over here. So let's bother about high spin and low spin. So high spin, low spin, because we're going to have to see the difference. D4, D4, D5, D6, D7, D5, D6, D7. Okay, so let's look at D4 high spin. D4 high spin, we have mu is equal to 2. If it's high spin, then it would have a spin of 2, so that's going to be 2, 2 plus 1, square root, multiples of Bohr magneton. That would equal 4.9 Bohr magneton. But if it's low spin, then it would be 2. It would be, let's see, 4. It would just be 1. So it would be 1. I caramba. It would be 1. 1 plus 1 square root ball magneton. That would only be 2.8. Okay, so we've got a huge difference for D4, whether it's low or high. All right, we navigated that. Let's have a look at D5. D5 high spin, we would have 2. And then if it's high spin, it would be 2.5. So 2.5, 2.5 plus 1, square rooted multiples of ball magneton, which is 5.9. Ball magneton, if it's low spin, it would be 2. That would be 1, 2, 3. That would be 0.5. So 0.5, 0.5 plus 1, square root ball magneton, that would be 1.7. Again, big difference. D6 high spin, so we're about halfway. That would be mu. So let's see, D6 high spin. That would be 2. So that would be 2, 2, 2 plus 1, rooted ball magneton. That would be 4.9. D6 low spin. That would be would have a spin of 0. So that's 2, 0, 0 plus 1, square rooted multiples of ball magneton. That would be clearly 0. Ball magneton. As soon as I said bar in my head, my brain wrote beta. That's just the way that goes. Ball magneton. Okay, 7, the last of the tricky ones. 7, spin only magnetic moment. We have 1.5 spins, so that's 2. 1.5, 1.5 plus 1, square root ball magneton. That's equal to 3.9. And if it's low spin, we have an overall spin of 1. So that's 2, 1, 1 plus 1, square root ball magneton. That's 1.7. Done it again. Brain said bar, my hand wrote beta. Oh, the psychology of it, it's fascinating. Okay, so there are the ones where we have to worry about high spin and low spin. Let's get back to D8, D9, and 10, where we don't. D8, D9, and D10. So D8, we have spin only magnetic moment is 2. We would have net spin of 1, so 1, 1 plus 1, square root ball magneton, which is 2.8. Ball magneton. 9, we have spin only magnetic moment, 2. Here the overall spin is a half, so 0.5, 0.5 plus 1, square root Bohr magneton, which is 1.7. And then finally, we have for D10, we have no net spin. So it's 0, 0 plus 1, square root Bohr magneton, which is 0 Bohr magneton. So here are all the answers, so you can practice them for yourself. These are crucial, remember, in the CFSE calculation type questions. We are headed dangerously close to the hour again. I don't know if I'll have a chance to do Jahn-Teller effect on this video. I had a couple of things I wanted to say about Jahn-Teller. Probably keep that to another video. Yeah, I think we'll keep the following to a separate video. So that will do us for now.